Hello and welcome back to the lab. Today on the bench we have a blank sheet of paper. I'm going to attempt to answer some questions that I've been getting a lot about capacitor replacements and a few other things. In this video we're going to tackle ESR and what is all this ESR stuff anyway. So if that sounds interesting, stick around and we will take a deep dive into the world of ESR and see if we can't shed some light as to what's going on behind the curtain. So this is going to be the second in a series. There'll be another video similar to this where we talk more in depth about capacitors themselves, failure modes of capacitors, things like that, and I'll get into some of the thought processes as to why I change out capacitors the way I do, what I'm doing, things like that. Seems to be a lot of different viewpoints on that. That is not this video. That will be a future video. This video we're going to discuss ESR, what it is, how to measure it, and somewhat more importantly, maybe what it is not. I am asked often if I have an ESR tester here in the lab. And I have an LCR meter right here that does have an ESR function and will test ESR for me. And I have Kelvin leads. Doing this off camera so you guys can't see me struggling with cords. So we have two Kelvin clips that run into the block of the ESR meter. And these do have some guarding voltages and things like that. But the thing with ESR and capacitors is it doesn't really matter that much until it does. To talk about that, let's talk about what ESR is, and we'll see if we can't shed some light on the subject. So if I have a capacitor, let's say we have a power source. We'll just draw a quick battery here real quick. We'll have V plus, V minus, and for the sake of argument, we'll have a polarized capacitor because we can. So we have a power source and we'll come off of here and we'll say some form of our load. That's a horrible resistor, but that's okay. This is why I use CAD programs for schematics. We have a power source that charges this capacitor, and then we go out to load. This would be a smoothing capacitor and a power supply. Now, we could replace this with a transformer and rectifier set, a few other things, get this capacitor to do something. If we did a transformer and rectifier set, so if we had transformer windings into a, I'm not going to draw the diodes, but into a rectifier, we are getting, in my neck of the world, because I'm on 60 hertz, we're getting 120 hertz pulsed DC out on the side of this. So that DC is rising and falling with the AC line, and I will turn on some of the test gear and we'll talk about this here in a second. I might do it safely with a function generator, but we'll see what we get into. When the lab cat decides that the rubidium standard is a chair, there's nothing I can do. She's done this. I don't know why she has taken to liking that spot, probably because it's warm. We'll see what we can do once it gets cold and I start the fireplace again. But she's about to go to sleep. At this point, all I can do is laugh. So what we would get is, if this would be ground, we'd end up with pulse DC at 120 hertz. Now, depending on what the load is, the capacitor will deal with these dips as holdover time. So when the voltage drops coming out of the transformer going through below the rail voltage, the capacitor is then delivering the current that the circuit needs until it gets the next charge pulse and the next charge pulse. This is where the ripple current rating of the capacitors are. This gets into ESR. So the faster these ripples come, the less the capacitor has to work current-wise, but it does have to work faster frequency-wise. The slower the ripples come, the more current the capacitor has to deliver, but it doesn't get hit as hard. So it's slowed down. So, and this really gets into, this really starts to matter in switching power supplies. One of the reasons capacitors is so reliable in older test equipment is we don't have switch mode power supplies. We're using linear power supplies, mains transformers, because in other parts of the world, I'm in North America, but in other parts of the world, this is actually 100 hertz because the input's 50 hertz. When you do a full bridge rectifier, it's double line frequency. Whatever the line frequency is, that's what you get for DC pulses. Our capacitor has to hold over our load, and we can show this. I'll set up some test gear. We'll do a small power supply, and we'll take a look. This is kind of what was driving me a little nuts with the previous with that power supply for the VTVMs. We can use a quick demo board here. Here's our power supply from the VTVMs again. This is still a Rev 2 board. If you haven't seen these videos, I get into some in-depth testing and things like that going through here, but we have both sides of our transformer into a full bridge rectifier. So we get pulse DC right here. Well, that feeds into our bulk cap. This is a protection circuit that's not here, and this is just the discharge resistor for this capacitor, because this is a very high quality capacitor. And even though it's 3 volts, I don't want to set this down on something and have it like spark through a meter probe or something like that. So I'm just going to put a very high value 1 meg, 10 meg, something like this, just to bleed this cap off when the meter gets shut down. So this smooths out the ripples so we get clean DC on the other side of the capacitor. It's at least the idea. My original design on this capacitor was woefully insufficient. If you haven't seen that video yet, sorry about the spoiler. It's back in the video log. That one's actually been released as of the recording of this video. This Rev 2 board has not, but that will be coming shortly. These are just 2 decoupling capacitors for the regulator IC, just to keep it stable. Nothing special here. This is what's doing the majority of the work. Also, given that this is a low voltage power supply, this is a 10 millifarad capacitor at 6.3 volts, but it only sees 3.3, so it's fine. So we have a ripple current. Now, the problem is, and where ESR becomes a factor, is in switch mode power supplies, the switching frequency went up, which means the capacitor, in theory, shouldn't have to, quote, work as hard. The problem is the currents went up like crazy. Here is a random computer power supply that I had sitting around the lab. This is one of my test supplies. I do have a build destined for this, but not yet. But this is a nice 1,000-watt power supply. Typically for my computer builds, I try not to do anything under 850 watts anymore, because the stuff's starting to get kind of crazy with power draws. As you're about to see, it gets a little stupid. So if we take a look, this is the load chart for this power supply. Now we have a total power of 1,000 watts, but if you've worked on computers for any amount of time, you know this splits out into about 12 or 13 different power rails. So it gets kind of crazy. Now for a computer, you have 5 power rails that are critically important. You have 3.3 volts, which is the main CPU drive, which ultimately gets knocked down to 0.9 these days. You have 5 volts. You have 12 volts, which is the main rail that everything pretty much hangs off of. and what we're going to talk about here in a second. You have a negative 12-volt rail, and then you have a 5-volt standby. So the difference is, so on the 5-volt active rail, I have about 25 amps. On the 5-volt standby, I only have 3 amps, which is fine. I'll zoom in on this chart here real quick. However, what I want to call attention to is right here. And that's not an exaggeration. So this is a 1,000-watt power supply. I have one of my computers has a 1,600-watt power supply. Most of your wattage comes from your 12-volt rail. So yeah, it's 12 volts, but it's 83.3 amps, and that's continuous. That's not spike. So this thing can slam out 83.3 amps continuous in a package that's smaller than the sheet of a piece of paper, 8.5 by 11 here where I'm at. So kind of small package. I mean, here's my whole project board. This is not a large supply by any stretch of the imagination. It's actually my 1,600 watt adds several inches to the front end. But the thing is, if you take a look in here, and I don't know if we can even see, I can see the bulk. You can see the bulk cap right in there. Those are the bulk filters in front of the switcher, but I don't see the output filters. Oh, they're hiding. They're hiding way down there. Let me see if I can, oh yeah, this will work. So there are my output filters. So they're much smaller caps down there. Those are the outputs, being the bulk ones up here. They're huge. So the problem is, though, I have those tiny capacitors, which are about this size, right? I have those dealing with 85 amps at 12 volts at full load. Now, 85 amps, I have people talking at the camera probably going, you'll never see 85 amps. It's fine. Don't worry about it. Some of the graphics cards these days, especially when you ask them to do something, like when I render video for YouTube on the CAD computer, you watch it suck some juice out of the wall. Now it renders video quite quickly. I mean, we're talking a 40-minute video for YouTube renders out in about 6 minutes. Lots of horsepower. But for those 6 minutes, it sticks a straw in the outlet and drinks it out. I can do some monitoring when I render this video and pin a comment to let you know how much it pulls out of the wall, because the UPS will tell me. The thing is, so computer power supplies will run about a 20 kilohertz pulsed wave. The problem is I'm dealing with 83 amps, even though it's 20 kilohertz, maybe 56. 56 is also a common. Helps if I can draw better or write numbers better. 56 is also a common switching frequency. So those output filters, they're getting pounded when the supply's working. This is where ESR becomes a huge deal. Because if I had a reasonable ESR in there, so with an ESR of 0.05 ohms and a current of 85 at full load, 85 amps, we get a power dissipated in watts in the capacitor of 361.5 watts. Now, that's a little unfair to this poor power supply and these capacitors, because you're not going to pull the full 85 amps out of the capacitor. I got the switcher that's still shoving current in too. But as you can see, we have a very heavy power rail in this power supply. Ish. I mean, I don't even think this is considered low ESR at this point. But at 85 amps, the cap dissipates a whole lot of power. This gets into dielectric and a couple of other things. This is a physical property of the capacitor. So a better way to look at it, it's drawn this way a lot. So you have the capacitor, and then you have the resistor. But a better way to look at it is you have the capacitor, and this is an internal resistance of the capacitor. So this is purely physics in the capacitor is what's causing this problem. And every power supply has this. So batteries have this. Inductors have this. Bench power supplies have this. The lower the ESR is on the power supply, the more power it can dump faster. So chemical storage actually has quite poor ESR. You can pull power out of a capacitor a lot faster than you can pull power out of a battery. I did some battery simulator testing and things like that, and that's actually one of the reasons why I have a battery simulator here in the lab, is because depending on the battery you're using, the ESR can vary wildly. And I've even done battery maps to help some people figure some things out, and I've gotten battery profiles for people to simulate it. That's one of the reasons why I have the source measure unit, because the source measure unit will take a couple of days, but I can do a ESR pack or an ESR plot of the discharge profile from the battery, because as the battery discharges, the ESR goes up. That in turn, if you keep a constant current coming out of the battery, that in turn means a drop in the voltage. Because if I have a higher series resistance, I'm pulling the same amount of current, the voltage has to come down. Everything's interrelated. So, with these high current, small physically, high current, high frequency switch mode power supplies, the output filter caps, not necessarily the bulk caps, because those are right off of the rectifier, those see 60 cycle. Not too bad. Now they get hit when the switcher goes, but they don't get hit as hard. The output caps on these get abused. It also has to do with the difference in power supplies for the vintage gear, having linear power supplies versus switching. Nice thing about switching power supplies is they're kind of small. So this is a pretty thin power supply. Still kind of big. I mean, my hands aren't small. There's a power supply. But this is a 240 watt supply. So there's a lot of power in here. I mean, we have thick cable, things like that coming out of here. This thing gets a little warm when it's running. But for the size package, it produces a lot of power, which is good. Because a 1,000 watt linear supply, that's a big iron in the transformer. Like, there's a lot going on there. Huge transformer, big output caps, heavy. Like, if you take a look at this, we'll go back to this. In the linear world, we're at 300 milliamps is what this thing can barely push. Actually, let me do the wattage calculation. So on this board, doing a quick wattage calculation, we have 450 milliwatts, 0.45 watts. We have 240 watts. So much beefier in the switching supply, but we do take that into, we do push some components pretty hard. So ESR with anything, if you have a supply, so we'll draw it this way. We'll have a voltage supply. We'll have a load resistor, so we'll have V load, ESR. So every supply will have some form of internal series resistance. Capacitor, inductor, power supply, bench power supply, battery, anything. And it's a limit as to if you dead short the supply, not that supplies are safe to dead short, how much current can I get out of it? Eventually the supply will limit itself, and it can no longer drive current. The voltage will fall, obviously, because it has to, because watts are conserved. Yeah, good way. Let me fire up a supply, actually. Okay, using my Rigel power supply and this power resistor decade box, I'm going to show what happens when I have dial in ESR. Now I'm using this as a load resistor. I'm asking the power supply for 500 milliamps. When I have no resistance dialed in, I'm getting my full 500 milliamps throughput. I don't like the way this demo is working. Let me get another decade box. Okay, I have an 8 ohm power resistor, and I have the decade box, and I want to get it one more meter. Okay, there we go. So we have from the power supply coming in down here, going through the decade box, which is currently set to zeros. We have that coming out, coming into the fluke meter, which is then going into the 8 ohm load. So what I'm going to do is I have the power supply set to give me 12 volts at a half an amp. So we do have our 500 milliamps here. Now I can play with the series resistance to show what happens to the current going through our load resistor. So you could look at the load resistor as just a sub-in for a high current amplifier or something like that, because this is all current based. The higher the current is, the more the ESR matters. So if we add an ohm of series resistance, nothing really happens, but we're also not soaking too much current. Something happened. Yeah, so even adding 9 ohms at a half an amp, it's not doing much. But if we go to in the tens of ohms, it does a lot. So if we add 10 ohms of series resistance, not too much. 20, there we go. Now we're starting to see some action. So this is just 20 ohms of series resistance. And bear in mind, this is straight Ohm's law because this is all DC. So the longer our cables get, the worse this gets. The heavier the load gets, the worse this gets. The higher the current out of the power supply, the worse this gets. We can even prove that because what will these resistors handle? The low resistors will handle 5 amps. So we'll ask it for a full 3 amps at 12 volts. So it's not needing the full 3 amps, but if I add, there we go, I'm already down. So that's just at 1.2 amps. So 1.4 amps DC, if I just add an ohm of series resistance, we're down to 1.2. 2 ohms, 1.1. And it's just going to keep dropping. So as our ESR goes up, our current carrying capacity or current delivering capacity goes down. So we can exaggerate this even further by going to 20 volts. All right, now I'm at 2.3 amps. Having a power decade box is kind of convenient. Right there, we just dropped 200 milliamps by adding an ohm of series resistance. So this is what's going on in the capacitors too. Now we're playing around at 3 amps. You can imagine this parameter at 85 amps like that computer power supply. So things get kind of squirrely pretty quick. So that's just 3 ohms of series resistance. We're down what? Oh yeah, almost half, 2.3 to 1.7. So this is what's going on in the capacitors. Obviously, this is a much exaggerated scale. However, depending on the circuit, this can matter, and especially as the current goes up, this gets crazy. Now, this dissipation factor is being dissipated as heat in this decade box. The problem is, that resistor is getting a little toasty too, which is fine. The problem is this dissipation, this voltage drop through the equivalent series resistance is actually heating the capacitors. That's kind of where that degrees C rating comes in, because the capacitors having internal heating dealing with this ESR. So as the ESR of the cap goes up, the dissipation factor of the capacitor goes up, which means it will self-heat internally more if you yank on the current a lot harder. So everything feeds back into itself. I'm going to give, oh yeah, that's getting a little toasty. I'm going to give this a rest, and I will get some high quality capacitors, both low ESR and normal, and we'll kind of check their ESRs. So I have two capacitors that I've gotten off the wall of capacitors. Both of them are 220 microfarads. One's a 35 volt, one's a 25 volt. The 35 volt is a low ESR series. The 25 volt is a normal series. So we'll set this up. Turn this over to ESR. That's dissipation factor, quality. Now I have to be in capacitor series. Why does this thing only want to go in capacitor parallel? Let me argue with this for a minute. Okay, so on the ultra low ESR, we're at 0.07 ohms. And this is setting for ESR at 1 kilohertz. Because ESR can also be frequency dependent. So this is the non-ultra low ESR cap. And this one actually has a little bit better ESR than the low ESR cap, but it's also a slightly lower voltage. But if I go to frequency and we dial this up to 100 kilohertz, well, one is the capacitor is not performing very well at 100 kilohertz, so this is a little fast for this capacitor. So let's drop back to 10 kilohertz. That cap really doesn't even like 10 kilohertz. Let's see what the... See what the low ESR cap does. Doesn't like those either. So 1 kilohertz, it is reading correctly, 208 with a 0.7. The other cap is 196 with a 0.05. So your ESR, especially with voltage, the higher the voltage the capacitor is, the lower the ESR, or no, I'm sorry, the inverse is correct. The higher the voltage the cap is, the higher the ESR is probably going to be. But that's also because the swing is a lot more. You can swing slowly, or you can swing small a lot faster than you can swing large. Your voltage velocities are drastically different as you increase the amplitude and frequency. Like I said, this rabbit hole gets kind of deep. So let me see if I can get a really big cap, what some of those snap caps say for ESR. So here is a similar sized 270 by 200 volt. Let's see what this cap's ESR is going to be. 0.08, not too bad. Let me get a really big cap. Okay, so I tried to get my some of the much larger caps that I have on the wall, and they overranged this meter. But I have caps up to 20,000 millifarads, Like, I have some pretty big caps, or 20,000 microfarads. This is on the other side of the fence, this is a very high quality poly cap, 47 nano. So if I clip this in here, 47 nanofarads. The ESR of this cap at 1 kilohertz test frequency is pretty good. 0.03, not too bad. But if I dial the frequency up, we're still saying 0.02, go up to 100 kilohertz. 100 kilohertz, we're at 500 nano, but our, see if I can get the glare off, our ESR is actually pretty good on that cap. But if I go down to 100 hertz, our ESR is 1.7, 1.9. So ESR can definitely be frequency dependent, and you want to pick the right type of capacitor for the location in the circuit. We're down to 0.3, 0.2. We'll hit the frequency again to send it to 120. Um, 468 nano, especially at 600 volts, this is way too slow. The cap will run out of juice. If I was trying to filter a 600 volt rail with this capacitor, there's not enough capacitance. It'll run out. So the meter's kind of lying to us right here. But in circuit, that capacitor would just it would run out of charge before the next charge cycle. So I hope that clarified a few things. Hopefully that made sense. This is a very complex topic, and this spider web's kind of everywhere. So I'm sure there's going to be questions based on this video. I will do what I can to try to answer those questions in future videos. I will have more videos on capacitors and things like that in the future, and we will keep going from here. In the meantime, take a look at the Amazon affiliate links in the description below if you'd like to support the channel. There's links in the description to do that through Patreon and PayPal. And subscribe if you would like me to keep making content. I see everybody in the comments in between videos, and I read every comment on the channel. So I will see everyone there. With that, I will see everyone in the next video.